Hi, I'm Jessica, and welcome to the second video in our crash course on proofs. In our first video, we looked at conjectures versus proofs and looking at defining conjectures. We also looked at some basic tools that you need to write a proof. But in this video, we're really going to concentrate on writing a proof completely. So to do that, we're going to be looking at two different examples. Let's get started. All right, let's look at our first example. We need to find the length of the segment A, which is right down here. And when we first look at this, you might see, or you might assume that triangle ACD is a right triangle and that AB is perpendicular to the side CD. If that were the case, it would make our life a lot easier. We could use something like the proportional mean theorem to find our segment A. So that leads me to a question about this. True or false? To find the measure of A in the diagram, we can use the proportional mean theorem. Remember that the proportional mean theorem states that in a right triangle, each leg is the proportional mean between its projection onto the hypotenuse and the whole hypotenuse. The answer is false. So let's look at why it's false. Now, in order to be able to use the proportional mean theorem, I have to look at this concept of the projection onto the hypotenuse. In other words, I need to be able to prove whether or not AB here is perpendicular to CD, which would give me a right angle at B. And to be able to do that, Pythagorean theorem is actually a really good tool, okay? Because that would prove if I can use Pythagorean theorem and have it apply to my triangle ABC here, then I know that I have a right angle triangle, and I can move forward with my proportional mean theorem. So, quick calculation with Pythagorean theorem. Remember that 108 squared has got to, 108 squared plus 90 squared has got to equal to 135 squared. Quick calculation on the calculator shows me actually that would not hold true in this case. 108 squared plus 90 squared does not equal 135 squared. So, triangle ABC is not a right angle triangle. That means that the side AB is not perpendicular to CD, which means that my proportional mean theorem isn't going to hold true in this case. So let's take a look at other options. Now, when I take a look at my diagram, remember I mentioned that there's a couple triangles, ACD, ABC, and ABD. I actually have three triangles here. Maybe they're similar. This might be something worth exploring. And before we do, I have another question for you. Which of the following minimal conditions cannot be used to prove that two triangles are similar? Is it side, angle, angle, side, side, or side, side, angle? The answer is side, side, angle. To be able to use two sides and an angle to prove similarity between triangles, this angle actually has to occur between the two known sides, and that isn't the case for side, side, angle. Otherwise, everything else that was listed is a way to prove similarity between triangles. So let's take a look at those and how they might apply to our three triangles here. Well, if we think about the concept of side, 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 and I look at my triangles, I see that for my triangle ABC, I know actually all three sides, so it would work for that triangle. But if I take a look at the other two triangles that I'd be comparing it to, I don't have enough information because I need all three sides on all of the triangles that I'm comparing. And it falls apart for ABD and ACD because of my missing length A. So side, side, side does not work. What about side, angle, side? Side, angle, side, I need a known side, which I have here, an angle, and another side. So that works for ABC. If I take a look at ABD, again, I have a side, I have an angle, and I have another side, so that works. But once again, it falls apart for ACD because I have a common angle, that'll be good, but I have one side, and then I'm missing information about that other side. So it's not going to work there. What about angle, angle? So we're actually going to try and prove that the triangle ACD is similar to the triangle ABD using angle, angle. Let's take a look at what we've got here. The first statement, or the first thing that I see here, is that I've got an angle at the vertex A, and it's the same angle that I have down here at the vertex C. And I know this because of that little line. That little line's telling me that the measures are the same. So those two angles are congruent. So I'm going to make the statement that the angle, there you go, the angle BAD is congruent to the angle ACB. All right. Now, to justify this, I'm going to use what's called by hypothesis, which is kind of another way of saying that it's given in the problem. And of course, that's exactly what happened here. They give it to me in the problem. So that's good. Another way that I can prove that angles are the same is to look for a common angle between my two triangles. And if I take a look at my triangle ABD and my bigger triangle ACD, then I notice that D here is actually common to both. So I'm going to focus on that. That'll be my next statement, that my angle ADB is congruent to the angle ADC. The justification for that is that it's a common angle to both. Now that I've proven that two angles are exactly the same measure on my triangles, I can state that my triangles are in fact similar. So my next statement is going to be just a repetition of what I wanted to prove up there. It's going to be that my triangle ACD is similar to my triangle ABD. And the justification for that is, of course, angle, angle. You might want to check with your teacher that they're okay with you using an abbreviation like that. Sometimes they want you to write out the full theorem, but in this case, we're going to leave it angle, angle. Now, before we go any further, I have a question for you because I'm kind of curious about the other triangle involved here. So my question is, true or false? The triangle ABC is also similar to triangle ABD. So rather than answer that question directly, we're going to see if we can prove it ourselves. Now, if I take a look at the information that I have available to me, when I compare my triangles ABC to ABD, I see that both of these have two known sides with an angle in between. So I'm going to try the approach of side, angle, side. And I'm going to start with the angle in both of these cases because that angle is actually the same angle. The angle at A is the same measure as the angle at C, so I can use that right here in this problem as well. So my first statement is going to start similar to my last problem, in that the angle BAD is going to be congruent to the angle ACB. And this is, of course, by hypothesis or given in the problem. Now let's take a look at those sides. So for the two triangles to be similar, my corresponding sides have to be proportional. So if I take a look at my first triangle, I have 135, which is my long side here, and it's going to correspond to the long side on my other triangle that I'm comparing it to. So I'm going to set it up as 135 over 200. And for these to be proportional, it has to be equal to the shorter side over its corresponding shorter side on the other triangle. In other words, it's got to be equal to 90 over 108. Well, if I use my calculator to figure this out, 135 divided by 200 is going to give me 0.675. 90 divided by 108 is going to give me 0.833. These two are not equal to each other. So in other words, I do not have proportionality. My justification here is that corresponding sides are not proportional. This being said, that statement is false. The two triangles are not similar to each other, so my final statement is going to be that the triangle ABC is not similar to the triangle ABD. And the reason for that is side, angle, side. So if I go back to that first proof that we did together, I've already proven that the bigger triangle ACD is similar to that smaller triangle ABD. So it's actually this one, because I've proven it, that I can use to set up a proportion of their corresponding sides to figure out what that length A is. And this is what I'm going to go ahead and do right now. So I've done that. I've set up my proportion. I have the measure of AB, which if I take a look at my diagram here, it is 108 centimeters. Corresponds to the measure of the length CA. So that's our 135. And that is going to be equal to the measure of AD, which is the 200 centimeters here, over the measure of the length CD. And this is just a little bit more complicated because I actually have to remember to add those two lengths together. So that's going to be over 90 plus A. All right, so that's the proportion set up. I've just got to solve for A now. So put in my cross product, 108 times 90 plus A is going to equal to 200 times 135. This, using my calculator and distribution, gets me to 9,720 plus 108A, and that's going to equal to 27,000. Now, you guys are all in Sec 4 or above, so I'm not going to bore you with the details on how to isolate for A, but that's what you're going to go ahead and do right now. I've already done it, so I know that A is going to equal to 160 centimeters. Your answer should match mine, right? And we know now that the missing length here, A, is 160 centimeters long. We're done. And we're ready for our second example. Let's read it together. In the figure, CE and AB are parallel lines. Point D lies at the intersection of AE and BC. Prove that D is the midpoint of segment AE. So in a problem like this, we take a look at it, and there's actually quite a few givens, and then there's maybe a couple of assumptions that we'd like to make. So one of the assumptions may be that these are congruent triangles. The problem with that is we can't actually assume anything. We're going to have to prove it. So to help us structure our proof, we're going to use a table like this. So in a minute, we'll fill in the hypothesis, conclusion. We've got our statements and our justifications to go with that. But before we get to that point, I'd like to ask you another question. Which of the following are not part of the initial hypothesis? If you answered C and D, you are correct. So let's take a look at that. So the first two statements that were made in my question were actually going to be our hypothesis. So that's A and B. Statement C, that's actually going to be what we're trying to prove. So that'll be our conclusion. And statement D, well, it hasn't been proven yet at all. So we'll get to that in our statements here. The hypothesis, remember, has got to be something that is given to us in the problem. So we'll take a look at our figure here and our problem, and we know that from the problem, CE and AB are parallel lines. So that is the first statement I'm going to make in my hypothesis. I'm going to write that the line CE is parallel to the line AB. I'm also given in my figure that the line segment CD is equal to the line segment DB, and I can see that because of the two little pairs of lines there showing me that they're exactly the same measure. So that's my next hypothesis statement right here. Measure CD is equal to the measure of length BD. All right, now for the conclusion. The conclusion is what I'm trying to prove. And my problem states that I want to prove that D is the midpoint of segment AE. In other words, I need to conclude that the segment AD is equal to the segment DE. So I'm going to write that right here as my conclusion. Measure of AD is equal to the measure of DE. All right. So now that I know what I want to prove, I've got to make a bunch of statements in order to prove it. One of the ways to prove that this statement is correct is to go back to the idea that these are congruent triangles. If I can prove that my two triangles are congruent to each other, then I can prove the statement that my measures are equal to each other, or in other words, D is the midpoint of AE. And there are a few ways that I can prove congruency in a triangle. Remember, side, side, side. I can also use angle, side, angle, or I can use side, angle, side. In this case, I'm going to go for angle, side, angle. The first statement I'm going to make in my situation is that the angle ECD is congruent to the angle DBA. So I'm going to write that right here. Angle ECD is congruent to the angle DBA. Now, the reason I chose to focus on this one is because I know that my lines CE and AB are parallel to each other. And if two parallel lines are intersected by a secant, then they form congruent alternate interior angles. In other words, because these two lines are parallel, then I know that my alternate interior angles here are equal to each other or congruent to each other. So my statement is correct. The next statement I'd like to go ahead and make is about the measure CD and BD here. It's given to me in the problem that these two are equal to each other. So I want to make sure that I include that in my statements here. Measure CD is equal to the measure BD by hypothesis or given in the problem. So now I have an angle and I have a side. Let's go for another angle here. And I notice that I have this angle EDC, and I also have a congruent angle here, ADB. So I'm going to write that those two angles are congruent to each other. EDC is congruent to angle ADB. I know this because if I have vertically opposite angles, they're going to be congruent to each other. Vertically opposite angles occur when you have these two straight lines crossing each other like that. So CB is a straight line and it is intersecting with the straight line AE. My argument would not work, or this theorem would not work, if I had a situation like this figure here, where you can clearly see that the lines intersecting are not straight. So IJ and FG are not straight, or particularly the IJ. I can't use this theorem to support that. So these will not be equal angles, not applicable. But in our figure, it is applicable. So we're going to go ahead and use that. That means I have what I'm looking for here. I have angle, side, angle. I can now go ahead with the statement that my two triangles are congruent to each other. So that is what I'm going to write here. I'm going to write that my triangle ABD is congruent to the triangle ECD. Make sure that looks like a D to you all. There we go. All right. And I know this because of angle, side, angle. Now, if I have two congruent triangles, that means their corresponding sides are going to be equal. So if I go back to my conclusion here, I have now proven that. And I can go ahead and make the statement in that the measure of AD is equal to the measure of DE. Because if two triangles are congruent, their corresponding sides are congruent. I have now proven that D is in fact the midpoint of AE. So that concludes our crash course on proof writing. Now, our crash course really focused on all geometric examples, but in reality, a proof can be written about any form of mathematics that you want. For example, we could prove that multiplying an even number by an odd number always results in an even number. You might want to prove that the product of the slope of two perpendicular lines is always -1. Or we could prove that the root of k is equal to k to the power 1/2. We might also want to prove that adding two odd numbers together always results in an even number. Really, a proof can be written about anything. It's going to be this, like the structure is always going to stay the same. What's going to change is the justifications that you use to support your statement. So the theorems that you pull from. This is because it really just depends on the problem that you're trying to prove. As with anything else, to get better at proofwriting, you really have to practice proofwriting. So to help you do that, we actually have a few exercises associated to this crash course that you're welcome to go ahead and try. I would encourage you to do that. Get better with your proofwriting skills, and I am going to see you guys next time.